The graph shows the deer population in a Pennsylvania county between 2010 and 2014. Assume that the population grows exponentially. When we read the graph, we should read everything, including the legend or any explanation. In this case, there are two variables. T is the independent and N is the dependent variable. T represents the years in this case, and N represents the number of deer, which is the deer population. And also, T is the years since 2010. And so when T equals 0, this T equals 0 corresponds to the year 2010. This also means that T equals 4 corresponds to the year 2014. The graph does not use the same scale for the t-axis and the n-axis, which is fine. A. What was the deer population in 2010? From analyzing the graph that we just did, we see that in 2010, the number of deer or the deer population is N of T is the number of years in 2010. So in 2010, T is 0. N of 0 is, in this case, from the graph, we go to T equals 0 and we go to the y-axis and we see that N is 10,000. And so in the year 2010, there were 10,000 deer. B. Find the function that models the deer population T. And so this function or this model is going to be a formula. And this formula is the formula of N in terms of T. We were told that the population is assumed to grow exponentially. And so we will use the exponential model. N of T equals N sub 0 e to the RT, where N sub 0 is the initial value. The initial value we found in part A, it was 10,000, so we substituted in right away. 10,000 for N naught, e to the RT. And so we took care of the parameter N sub 0. We still need to find R, but that is where the second piece of information comes in. On the graph, the points imply that when T is 4, N of 4 is 31,000. And so if we were to plug 4 into this function, even though it is incomplete because we still don't know what R is, if we plug T, which is 4, into this equation, we need to get 31,000 because, again, the point is on the graph, so it satisfies the equation. From there, we should be able to find R. First, we divided by both sides by 10,000 to get e to the 4R. R times 4, 4 times R equals 3.1. 31,000 divided by 10,000 is 3.1. We then ln both sides of the equation because we need to get to R in the exponent. And so 4R equals ln of 3.1, where R is ln of 3.1 over 4. If possible, we want to hold on to this number ln of 3.1 over 4 as long as possible. But if we want to use the decimal number for R, we should round it to at least 4 decimal places, which is 0.2829. It is probably better to round it to 5 decimal places, which is 0.28285. And so the equation for the deer population is N of T equals, the initial population is 10,000, E is E, R is now 0.28285, and T is being multiplied to r. This is the exponential model. Part C, what is the projected deer population in 2018? Remember that t is the number of years since 2010, so we cannot plug in 2018 into this equation. T is not 2018, but in 2018, t is 8, because t is the number of years since 2010. We then plugged in 8 into the equation or the model or the formula that we just found. 10,000 e to the 0.28285 times 8, still in the exponent. This would give us 96,100. And lastly, estimate how long it takes for the population to reach 100,000. After 8 years, the deer population reached 96,100, and so we're almost there. And so when exactly? To do that, we set n of t equals 100,000 equal to 10,000 e to the 0.28285t, and we isolate t. First, we divide it by 10,000 from both sides of the equation to get 10 on the left-hand side. 100 divided by 10. The right-hand side is now e to the 0.28285t. We then ln both sides of the equation to get ln of 10 on the left-hand side, and on the right-hand side, ln of e collapse, and we'll get 0.28285t. It is now clear how we're going to get t. T is ln of 10 divided by 0.28285, and this is roughly 8.14. This is the number of years. And so a little bit after 8 years, the population of the deer will reach 100,000.